We've been talking about muscle contraction, but so far almost everything we've talked about has happened at the cellular or molecular level. For example, an action potential stimulates the release of calcium. Calcium causes contraction. An action potential lasts only a couple milliseconds, and the resulting calcium release and force generation only lasts maybe 100 milliseconds. In the real world, I've got to contract my muscles over seconds or even minutes, and I have to control the amount of force I produce. For example, if I want to throw that up in the air, that's different than if I just want to lift it. And Newton likes to chase snow. He can sometimes even find it. In this video, we're going to talk about how we control the amount of force we produce with the muscle, which is also going to help us explain how we control the duration of muscle contraction. At its most basic level, the amount of force generated by a muscle is controlled by the number of cycling cross bridges. If we use a model where every myosin molecule exerts the same amount of force, then the only way we increase the amount of force is by using more myosin molecules. That can only happen in two ways. Either one, we can use more myosin molecules in a specific muscle fiber, or we can recruit more muscle fibers. In the first case, the way we would recruit more myosin molecules in one fiber is to increase the amount of calcium surrounding the myofibrils. If there's more calcium, there will be more exposed myosin binding sites, and more myosin molecules can actively form cross bridges. This is going to be called temporal summation because calcium levels rise as action potentials are fired faster or in a shorter period of time. Spatial summation is the second way we could recruit more cross bridges, and that's simply using more muscle fibers. If we're using more muscle fibers, we can use more cross bridges. We'll talk about temporal summation first. An action potential results in generation of force that lasts maybe 100 milliseconds. The force generated by a single action potential is called a twitch, and it's proportional to the number of cross bridges that are formed. So imagine that enough calcium is released that half of the myosin binding sites on the thin filament are exposed. Then maybe half of the available cross bridges could cycle. If calcium levels doubled, all of the myosin binding sites would be exposed, and the fiber could generate twice the amount of force. But then if every action potential is the same size, how are we going to change the amount of calcium released in response to the action potential? Well, if calcium is released and then pumped back into the SR before the next action potential is fired, then when the process repeats, it'll look exactly the same. But now imagine an action potential occurs before all the calcium is pumped back into the SR. If that happens, the calcium released in response to the second action potential is added to whatever was left in the sarcoplasm. As action potentials get closer and closer together, calcium levels in the sarcoplasm rise because calcium is released faster than it can be pumped back into the sarcoplasmic reticulum. At a certain point, calcium levels are high enough that all of the myosin binding sites on actin are exposed, and we'll have cycling of the maximum number of cross bridges without relaxation between twitches. This is a state called tetany, a state of sustained muscle contraction because all of the myosin binding sites are exposed. Now, there's a non-obvious fact embedded in this explanation. Calcium is released only in response to an action potential. If we depolarize the muscle fiber and it stayed depolarized, calcium is released in response to the initial depolarization, but then calcium release stops, the calcium is pumped away from the myofibrils, and the muscle fiber will relax. The muscle fiber has to repolarize and depolarize again for calcium to be released again from the sarcoplasmic reticulum. The refractory period in skeletal muscle dictates the repolarization after the first action potential, and the refractory period determines how fast action potentials can be fired and the rate at which calcium can be released. Okay, so temporal summation. The amount of force generated by a muscle fiber increases as the frequency of action potentials increases. That's because there's more sustained calcium release, exposing more myosin binding sites on actin and allowing more cross bridges to cycle. What about spatial summation? So far, our images have focused on a single axon terminal and the motor end plate of a single muscle fiber. In reality, the axon of a motor neuron has a lot of different branches. Each of the branches travels to a motor end plate on a different muscle fiber. When a motor neuron fires an action potential, it's going to turn on a group of muscle fibers. A motor neuron and the collection of muscle fibers it stimulates is called a motor unit. Now, you can see in my drawing that the muscle fibers in any given unit are spread throughout a muscle in different fascicles. This means when a motor unit fires, the force generated is spread throughout the muscle and not focused in just one place. In large muscles like the rectus femoris, a motor unit might contain 1,000 or more muscle fibers. In muscles that exert fine control, like eye muscles, a motor unit might have only 10 muscle fibers or maybe even fewer. Even in the same muscle, motor units can have different number of fibers, and the fibers can be of different diameters. Some motor units might have fewer fibers, and the fibers could be of smaller diameter. These motor units would produce less force because there are fewer available cross bridges. On the other hand, those narrower muscle fibers typically have a lot of mitochondria and a better blood supply, so they can make ATP pretty quickly. Because those fibers can restore ATP as it's used up, they don't get tired very fast. So even though the smaller motor units don't make as much force as larger ones, they can contract over longer periods of time. The soleus is a muscle that helps us maintain posture throughout the day, and this muscle has smaller motor units that don't get tired that fast. Other motor units might have a larger number of fibers, and the fibers can be fatter diameter. These motor units form more cross bridges, so exert more force, but the muscle fibers don't have as many mitochondria, and they don't have as good a blood supply, so they get tired faster. The gastrocnemius, which is just superficial to the soleus, is more of a sprinter's muscle. There are a lot of larger motor units that can exert more force, but the units fatigue over a shorter period of time. So the gastrocnemius is a muscle we might use more in a sprint as opposed to the soleus, which we use throughout the day. Now, if I want to use a muscle to accomplish a task, I'll begin contracting the muscle by recruiting the smallest motor units that exert the least amount of force. So let's say, for example, I'm drinking this glass of water. I'll start with the smallest motor units and recruit larger and larger units until I'm able to lift the water and execute the desired task. Once my brain is satisfied with the strength of contraction, there's no need to recruit larger motor units. On the other hand, if I want to lift something really heavy, I'll still start by recruiting the smallest motor units, but recruit larger and larger motor units until I'm able to either lift what I'm trying to lift or I can't accomplish the task. So when I'm exerting maximal muscle contraction, I'm trying to draw on every available motor unit. Spatial summation refers to recruiting more muscle fibers to increase the number of active cross bridges. All right, to sum it up, a muscle generates more force by increasing the number of active cross bridges. Force can be increased by either temporal or spatial summation. Temporal summation refers to increasing the frequency of action potentials, which increases intracellular calcium, exposes more myosin binding sites on actin, and results in more active cross bridges. Spatial summation refers to using more muscle fibers. The body starts contraction by recruiting the smallest diameter muscle fibers that exert the least amount of force, but they don't get tired very fast. And we continue to recruit larger and larger motor units as we need to exert more force. In the next videos, we're going to move even further from the lab as we start talking about different types of muscle contractions and how muscles move bones around joints.